Right now, at the very bottom of the Pacific Ocean, in a place so deep that sunlight is mathematically impossible, a number on a screen is rising. And that rising number is threatening to rewrite every single textbook we have ever written about the origins of life on Earth. If oxygen can be made in total, absolute darkness, then one of our favorite, most trusted signs of life isn't a sign of life at all. It is a question mark. Tonight, you and I are stepping onto the deck of a research vessel. The winch is already screaming. A braided steel cable is sliding into the pitch-black water of the Pacific Ocean, dropping like a thread into an endless needle. We are heading down, kilometers deep, toward a place where the very concept of daytime is meaningless. And somewhere down there, near the freezing, crushing bottom, the oxygen sensors are spiking. The deck of the ship is vibrating violently under our boots. You can smell it, the thick salt air, the heavy diesel exhaust, the sharp, almost bloody metallic smell of a wet steel cable. Someone in the corner of the control room calls out the depth. Someone else watches a bank of glowing monitors with a calm that feels entirely practiced, like they have learned to wear their anxiety as a uniform. As the remotely operated vehicle, the ROV, tips over the stern and disappears beneath the whitecaps, the real question lands heavily in the room. What does it actually mean, chemically, to breathe on a planet? And why did we ever, for a single second, assume that sunlight is the only way to manufacture that breath? Because let's be honest, oxygen is far more than just chemistry to us. Oxygen is intimacy. It is the burning in your lungs when you sprint to catch a train. It is the warmth of firelight pushing back the dark. It is the razor-thin line between waking up in the morning and not. For centuries, we have treated oxygen like a definitive verdict. Is oxygen present on a planet? Then life is probably there. Is oxygen absent? Then life is probably not. But here is the cold, hard truth. The ocean does not care about our poetry. The ocean does not care about our metaphors. The ocean cares about one thing and one thing only: gradients. Differences in energy, differences in electrons, differences in chemical hunger. And that is exactly why this story is not just about the deep sea. This is a story about how human beings decide what is real. It is a story about whether a single, anomalous rising number on a glowing screen should be allowed to completely shatter and rebuild a scientific worldview. So, here is the incredible scientific claim that we are auditing, right here, right now, together. In vast stretches of the abyssal seafloor, kilometers below the deepest reach of a single photon of sunlight, oxygen concentrations appear to be mysteriously increasing, even though biological photosynthesis is completely impossible. The phrase the scientific community is starting to whisper is dark oxygen. It sounds like poetry. It sounds like a science fiction novel. But it might be sheer brute force physics. Or it might be an instrument being entirely fooled. To understand this, we have to understand the setting. Beneath our ship lies the Clarion-Clipperton Zone. This is a massive, sprawling patch of the central Pacific Ocean, stretching thousands of miles between Hawaii and Mexico. And down there on the abyssal plain, the seafloor is carpeted with something very strange. They are called polymetallic nodules. If you look at them on camera, they just look like lumps of coal. Like dark, rounded pebbles scattered across an endless, silent plain of sifted flour. But these are not normal pebbles. They are ancient, unbelievably slow-growing geological concretions. They grow maybe a few millimeters every million years. And they are staggeringly rich in manganese, iron, nickel, copper, and cobalt. Chemically speaking, these nodules are complex. They are almost like geological hard drives, silently storing the entire redox history of the Earth's oceans. Now wait. What do I mean by redox? Redox is just a chemist's shorthand for reduction and oxidation. It is electron bookkeeping. The entire universe, and nature itself, runs on strict electron accounting. Some atoms want to steal electrons with the absolute desperation of a starving person wanting food. We call that oxidation. Other atoms are incredibly desperate to give their electrons away. We call that reduction. And if you take the right materials, and you connect them through a conductive path, and you drop them into a salty electrolyte, like, say, the seawater of the Pacific Ocean, you have just built a battery. Whether you meant to or not. And that brings us to the core tension of this entire mystery. Why are we so obsessed with oxygen in the first place? We treat oxygen as the ultimate biosignature, a giant, neon clue for life, because oxygen is highly reactive. Oxygen does not like to be alone. It does not like to stay free. If you leave free oxygen alone, it aggressively wants to latch onto things and disappear. It turns iron into rust. It turns carbon into carbon dioxide. It bonds with hydrogen to make water. Because it is so incredibly reactive, if you look at a planet and you see a massive amount of free oxygen just floating around in its atmosphere or its oceans, you automatically assume that something must be actively, continuously making it. Something is fighting a relentless war against oxygen's natural tendency to vanish. And on planet Earth, for the last 2.5 billion years, that something is mostly oxygenic photosynthesis. Plants, algae, and cyanobacteria use the sheer radiant energy of sunlight to violently split apart water molecules. They release the O2 into the air, and they stash the leftover electrons into complex sugars to survive. That is the story we all grew up with. That is the biological dogma. That is the fundamental premise around which we have spent billions of dollars building space telescopes and planetary probes. But down in the crushing depths of the abyss, the known universe, version of the deep ocean, oxygen is supposed to do the exact opposite. In total darkness, right above the sediment, oxygen is supposed to be consumed. Microbes breathe it in. Slowly decaying organic matter eats it up. Chemical reactions absorb it into the mud. If you put a sealed chamber over the mud down there, the oxygen levels should strictly, predictably, relentlessly go down. The only way it stays replenished is through slow, massive ocean currents bringing cold, oxygen-rich water down from the surface. So, if we put a sealed chamber down there, and the oxygen number starts going up, that is like walking into a blazing hot sauna and watching frost magically form on the wooden benches. It defies the basic thermodynamic expectation of the room. It does not mean it is physically impossible. It just means that either we have completely missed a massive, invisible source of cold, or the thermometer is lying to us. And you are not here today to be spoon-fed a neat little conclusion. You are on the dive team. You are an auditor of reality. Every single time that number rises on the monitor, we have to stop the ship, pause the mission, and ask 3 ruthless questions. 1. Is this real oxygen? 2. Is this real active production? 3. Is this real physics, or are we being tricked by rogue ocean currents, faulty calibration, or just sheer, desperate wishful thinking? The ROV is falling through the black water now. We are watching a descent that takes agonizing hours, and that kind of waiting does something strange to the human brain. Up here on the surface, the world is full of comforting reference points. You have the horizon, the angle of the sun, the gentle rhythm of your crewmates talking. But down there on the live feed, there is only depth, pressure, and time. The screens show absolutely nothing at first. It is a void. Just a blizzard of particulate matter, what marine biologists call marine snow, drifting endlessly past the camera lens. Then, suddenly, the powerful LED lights of the ROV strike the bottom, turning the infinite darkness into a harshly lit tunnel. And you feel it in your gut. This subtle, heavy shift. The realization that the deep ocean is not empty at all. It is just withholding its secrets. Here is a thought experiment I want you to hold in your mind, like a heavy, cold tool in your pocket. Imagine that you and I are standing there, holding this incredibly expensive oxygen sensor in our bare hands. Right now, 2 entirely different worlds are possible. In World A, massive amounts of oxygen are actually being created down there, in the pitch black, crushing deep, generated by strange chemistry that we have never fully respected or understood. In World B, the number on the screen is rising because the instrument is simply being lied to. It is being squeezed by pressure, warped by temperature, or fooled by a hidden flaw in its own engineering. This entire scientific investigation, This entire audit is about learning exactly how to tell those two worlds apart. Now, before we get to chase the exotic and the glamorous, we have to pay our respects to the boring. Science does not advance by jumping to the wildest conclusion. Science advances when we eliminate the boring explanations with ruthless, systematic kindness. So, let's build our courtroom. Let's put the data on the stand. What could possibly fake an oxygen rise at these abyssal depths? Exhibit A: Physical mixing. Let's say a rogue eddy of cold, oxygen-rich water just happens to slide past our sensor. Like a thin, invisible river winding through the deep ocean. That influx of fresh water can mimic local production. The ocean is not just a static bathtub, it has highly complex layers, deep-sea boundary currents, and swirling micro-eddies. Oxygen concentrations can vary wildly over surprisingly small distances. Furthermore, if our incredibly heavy robotic vehicle stirs up the water, if its thrusters change the boundary layer of fluid right near the sensor face, the reading can falsely spike even if nothing new is actually being made. Exhibit B: Sensor artifacts. Drift is a quiet, devastating villain in the world of oceanography. Many of the sensors we use, like optical optodes or traditional Clark electrodes, can slowly change their baseline over time. Imagine calibrating a delicate instrument in a comfortable, sunny laboratory at 1 atmosphere of pressure. Now take that same instrument and throw it beneath 4,000 meters of salt water. You are subjecting it to hundreds of atmospheres of crushing pressure. That pressure can warp the physical properties of the sensor's membrane. It can alter the chemical response times. It can literally crush the chemistry happening inside the probe. Temperature fluctuations matter enormously too. And then there is the ultimate nuisance: biological fouling. Tiny biofilms and microscopic particles can stick to the sensor face, turning a clean, precise electrical measurement into a messy, unpredictable biological negotiation. If you have never sat in a lab and watched a highly expensive piece of equipment slowly decide that it has its own independent opinion about the universe, you haven't lived. Exhibit C: Deep Sea Biology. Though this is the least likely culprit in the true abyss. We know that photosynthesis is entirely off the table at these depths. There are zero photons. But biology is infinitely clever. Microbes can store strange oxidants. They can form complex films. They can create tiny, isolated microenvironments. Some organisms, in moments of stress, can even generate highly reactive oxygen species, like hydrogen peroxide. In principle, the slow decomposition of these oxidants could release small amounts of oxygen gas without any sunlight. But here is the catch: biology still has to balance its thermodynamic books. Energy does not just vanish or appear out of nowhere, it simply changes costumes. If biology is making oxygen, it is paying a massive energy tax to do it, and we have to figure out where the funds are coming from. Exhibit D: Strange chemistry. You can definitely release trapped oxygen from porous materials. You can decompose surrounding oxidants. You can even have a process called radiolysis, where natural, low-level radiation from the Earth's crust actually strikes and splits water molecules into reactive fragments. But again, the true scientific question is never, can anything weird happen? The true question is, can it happen at the massive rates, and for the sustained durations, implied by these rising measurements? Because that, right there, is the difference between a minor chemical curiosity and a planetary-scale budget. And now, the descent of our ROV is finally over. The high-definition downlink footage fills the main screen. The robotic arm of the sub reaches out. The seafloor appears before us, incredibly flat, deathly silent, almost entirely lunar. It is a vast plain of beige sediment with a soft texture, exactly like sifted flour. And then, we see them. The scattered nodules. The pebbles that aren't pebbles. Metallic, ancient, shaped by impossibly slow chemistry over millions and millions of years. Under the harsh glare of the LEDs, they look oddly organic. They look like sleeping organs resting in the mud. Someone in the control room zooms the camera in. You can see delicate, incredibly faint tracks in the silt where a bizarre, pale animal passed by weeks, maybe months ago. This place is not dead. It is just remarkably, fundamentally quiet. And then, The oxygen trace on the monitor ticks upward. There is a specific moment that never shows up on the scientific graphs or in the published papers. It is a moment that happens purely in the human body. The control room goes entirely still. It is the kind of heavy stillness where even the people who are paid to talk for a living simply stop. You suddenly feel the breath in your own lungs, acutely aware of exactly what is at stake. Because this is the exact molecule that we have tied our entire understanding of life to. We tie oxygen to sprawling green forests, to massive algae blooms visible from space, to the deep history of Earth's atmosphere. Yet the cold, hard number on the screen says, there is more oxygen, right here, right now, in the pitch dark. How could oxygen actually accumulate right at the seafloor near these rocks? That is the core mystery of the benthic lander experiments. In these tests, scientists dropped massive sealed chambers over patches of the seafloor containing these nodules. They sealed off the water. They expected the oxygen to slowly drop as the sediment breathed. Instead, over 47 hours, the oxygen levels surged. The honest way to deal with this is not to fall instantly in love with an exotic explanation. The honest way is to cross-examine the measurement like a hostile witness. Let's go back to our courtroom. Let's assume the researchers are paranoid, brilliant, and skeptical. How do they prove the sensors aren't lying? First, you don't trust one sensor. If your optoid is drifting, you bring a completely different physical technology. You bring a Clark electrode. You mount them side by side. You independently calibrate both of them in high-pressure chambers that perfectly mimic the crushing deep sea. You do not ever ask one single sensor to testify alone. Second, you run a null control. This is the bedrock of science. You take the exact same vehicle, the exact same sealed chamber, the exact same timeline, and you place it over a patch of the seafloor that is completely empty. No polymetallic nodules. Just mud. If the oxygen rise still happens over the empty mud, then the nodules are completely innocent. They are irrelevant. We would have to look elsewhere. But if the oxygen only spikes when the chamber is sealed over the nodules, the rocks are guilty. Third, you do a chemistry cross-check. You don't just rely on electrical sensor readings. You physically capture samples of that deep sea water, bring them all the way back to the surface, and run them through a mass spectrometer. You look at the actual dissolved gas. You look at oxygen isotopes, an independent, chemical witness that fundamentally does not share the same engineering biases as your electronic probe. Here is the incredibly uncomfortable thing about real science. Absolutely none of this process is glamorous. These are the tedious, unsexy, grueling rituals that protect human beings from being seduced by our own fascinating graphs. But the researchers did all of this. They ran the null controls. They swapped the sensors. They did the lab incubations. They checked the isotopes. And if this dark oxygen survives this brutal cross-examination, and the current data suggests it is surviving, we finally earn the right to ask the most dangerous question of all. Where is the sheer electrical energy coming from? Making oxygen from plain water is energetically brutal. In a laboratory, if you want to perform electrolysis and split water, you typically need to hit it with at least 1.23 volts in perfectly ideal conditions. In real, messy systems, you often need significantly more voltage because of something called overpotentials. You can think of an overpotential as the massive extra push you need to get a stubborn chemical reaction moving. It is exactly like the intense static friction you have to overcome before a heavy box finally slides across a hardwood floor. So, if water is being split at the bottom of the ocean, the seafloor desperately needs a massive power source. It cannot be sunlight. It obviously cannot be a wall socket. It has to be something else entirely. This is the exact moment where the polymetallic nodules step out of the shadows and become our prime suspects. Hypothesis 1: Natural galvanic cells. The battery rock idea. I want you to picture one of these nodules. Do not picture it as a solid, boring pebble. Picture it at the microscopic level as a chaotic patchwork quilt of highly reactive mineral phases, manganese oxides tightly mashed against iron hydroxides, laced with trace metals like nickel and copper. Every single one of these different minerals has a completely different appetite for electrons. If two of these mineral phases have radically different electrochemical potentials, and the salty seawater flows into the microscopic cracks between them to connect them, electrons can physically flow from one side to the other. The seawater is acting as a perfect electrolyte. The entire nodule literally becomes a battery. Now, this is not a neat, clean, wrapped AA battery you buy at the store. It is an incredibly messy, corroding, constantly self-modifying battery built by geological time. If this wild theory is true, what exactly should we be able to see? Well, we should be able to take a multimeter and measure actual voltage differences across the surface of a single nodule. Maybe just a few millivolts, or maybe massive, transient spikes depending on the microstructure and the catalytic sites. And guess what? When researchers brought these nodules up and tested them, they measured voltages across their surfaces of up to 0.95 volts. That is staggering. It is just shy of the magical 1.23 volts needed to split water, but with microscopic variances, it is well within the realm of possibility. Furthermore, if water splitting is truly happening, we shouldn't just magically get oxygen. The universe demands a counterreaction. Somewhere on that rock, we should see measurable hydrogen gas being generated, or a severe reduction of metal oxides, or highly localized, intense shifts in the pH of the water. How do we falsify this? How do we break the battery theory? You measure in situ electrical potentials with microelectrodes. You hunt for hydrogen gas in the exact boundary layer of the sediment. If oxygen rises and there is absolutely no hydrogen, you have a massive thermodynamic accounting problem. Even better, you can electrically isolate the nodules. You coat them in a perfectly non-conductive epoxy layer, leaving only a tiny defined window open to the water. If the mysterious oxygen production immediately stops the second those conductive pathways are interrupted, the electrochemistry explanation suddenly gains massive, undeniable weight. But let's be thorough. What else could it be? Hypothesis 2: Reactive oxygen release. The hidden reservoir idea. Maybe the rocks aren't actively manufacturing fresh oxygen. Maybe they are just leaking it. The surfaces of these nodules are incredibly chemically active. They can host a whole family of oxidized species, things like peroxides, superoxides, and high-velocity manganese compounds. Under changing conditions, these stored compounds could rapidly decompose, breaking down and releasing their trapped O2 into the water. Think of the nodule like a rigid sponge that has been thoroughly soaked in reactive oxygen for millions of years. When we disturb the pressure, or the temperature, or the water chemistry by dropping a giant robotic lander on it, we are effectively squeezing that sponge. If that is true, what do we predict? We predict massive pulses of oxygen that quickly decay over time as the finite reservoir simply runs out. We predict that the oxygen spikes are highly dependent on physical disturbance. How do we falsify it? Long-duration incubations. If the oxygen levels just keep rising, steadily and relentlessly, over days and weeks without ever depleting, then a finite hidden reservoir becomes mathematically impossible. The rock isn't leaking. It's building. So far, we have been extraordinarily careful. We have audited the sensors. We have tested the batteries. We have squeezed the sponge. But right now comes the exact moment where a massive, paradigm-shifting new picture tries to form in our minds. You are staring at the raw footage of these nodules on the screen. They sit there in the mud like inert, dead stones. But then you imagine the microscopic, atomic view. A dense, chaotic forest of mineral grains. Highly conductive microscopic filaments. Razor-sharp junctions where one metallic phase aggressively touches another. Tiny catalytic sites acting like microscopic stages where bizarre chemical reactions can finally perform. And you realize the truth: a rock is not just a rock. A rock is a circuit. The manganese and the iron oxides become the electrodes. The salty ocean becomes the perfect liquid electrolyte. The microscopic cracks become the intricate wiring. And biofilms, deep-sea bacteria living on the surface, could become living transistors, actively shuttling electrons back and forth, adjusting the resistance of the stone itself. Suddenly, the abyssal seafloor completely stops being dead terrain. It starts looking like a massive, globally distributed, incredibly slow power grid. And when you realize that, the entire scientific question changes. The question is no longer, can rocks make oxygen? The question becomes, exactly how much chemical free energy is quietly, relentlessly flowing through the dark corners of the Earth where we simply never thought to measure? This is where a good, rigorous audit becomes the actual birthplace of radical innovation. Because even if the original dark oxygen claim turns out to be slightly wrong, it points a giant glaring spotlight at a massive blind spot in our science. We rarely ever map the electrical life of the seafloor with the same seriousness that we map its temperature or its salinity. We treat deep ocean sediments like passive, dead backdrops. But what if they are incredibly active circuits? Slow, persistent, and largely invisible to the human eye. So, as an elite auditor of science, I want to propose an innovative, theoretical hypothesis right here that can either live or die by future measurements. Let's call it transient electrolysis driven by biofilm-mediated microscale redox disequilibria. The main objection to the battery rock idea is usually very straightforward. You just can't get enough voltage. 0.95 volts is not 1.23 volts. The bulk, average potential of the rock seems too small to overcome the immense overpotentials required for oxygen evolution. But what if the seafloor isn't a smooth, uniform battery at all? What if it is a jagged landscape of intense microevents? Imagine a razor-sharp mineral junction on the nodule that geometrically concentrates electric field lines. Imagine microscopic conductive filaments that intermittently connect different metal phases, acting exactly like a flickering switch. Now, add biology. Imagine deep-sea bacterial biofilms mediating the electron transfer, physically altering the local chemistry at the atomic scale to severely lower the overpotentials, making the chemical reactions vastly easier to achieve. In this new view, the nodule does not provide a steady, boring 1.23 volts like a plastic power supply in a high school physics lab. It provides rare, intense, highly localized moments where the reaction becomes fleetingly possible. It is exactly like lightning in a storm cloud. If you average the electrical charge over the entire sky, the sky looks completely calm. But in one specific, highly localized channel, the voltage spikes, the resistance drops, and the air violently tears apart. The nodules are creating chemical lightning. How do we verify this wild idea? You deploy advanced microelectrode arrays to map the oxygen gradients at the millimeter scale around a single nodule. You look for intense, highly localized hotspots of production. You simultaneously map the electric potential and the pH at the exact same microscopic resolution. If oxygen is being manufactured right there, the chemistry around those specific tiny hotspots should absolutely betray it. Massive pH shifts, wild redox changes, and detectable hydrogen bleeding into the system. Then, you bring these exact nodules into high-pressure laboratory mesocosms. Miniature abyssal oceans built of thick steel and thick glass. You test their dependence on the rock's composition, the surface area, and the presence of biofilms. You compare raw, wild nodules against sterilized, dead nodules. You compare them against nodules painted with a coating that strictly blocks catalytic sites. If the oxygen production immediately collapses when you block those specific microscopic surfaces, you have found the exact stage where the play happens. And how do we brutally falsify it? If our high-resolution maps show absolutely zero oxygen production at the surface of the rock, only simple fluid advection patterns moving water around, this mechanism utterly fails. If the isotopic composition of the oxygen gas cannot be mathematically reconciled with water-derived oxygen, it fails. If inert, plastic rocks of the exact same shape and roughness somehow produce the exact same oxygen signature, then the metallic nodules are not the cause. The hypothesis dies. Cleanly, quickly, and with dignity. This is exactly what I love about a truly great scientific audit. It does not just hand you a yes or a no. It teaches us exactly what kind of evidence is heavy enough and strong enough to actually move a human belief. Now I want you to zoom out. All the way out. Back up on the surface of the ship, the bright daylight suddenly feels entirely different. It feels less like the magical source of all life, and more like just one of many different ways a planet can pay its energy bill. Because life, at its deepest, most fundamental core, is not about sunlight. Life is about sustained free energy flow. Life is just an organism finding a gradient, a difference in energy, and ruthlessly exploiting it to turn that energy into structure, memory, and motion. If dark oxygen is real, even in small, incredibly localized pockets, Earth's system science changes overnight. First, our deep-sea oxygen budgets might desperately need an entirely new abiotic source term. The chemistry of the ocean sediment could look entirely different than we thought. Entire microbial ecologies could be shaped and sustained by tiny puffs of oxygen that appear not from the sun, but from the slow, grinding electricity of rocks. That is not a minor footnote in a textbook. That is a fundamental reshaping of what we think the planet is doing while we are asleep. Then, we face the massive ethical and economic consequences. Polymetallic nodules are not just scientific curiosities. They are the target of a massive, impending deep-sea mining rush. Companies want to drop giant robotic harvesters down there to vacuum up these rocks for the nickel and cobalt we need for electric car batteries. But if these nodules are acting as geological batteries, actively sustaining deep-sea chemical networks, then they are not just inert rocks sitting in the mud. If mining rips them away, the environmental impact might not be strictly limited to basic habitat loss. It could completely alter the microredox landscapes, sever the local oxygen availability, and utterly crash the subtle energy economy that deep-sea ecosystems have adapted to over millions of years. Even if the dark oxygen effect is small, the sheer principle is terrifying. Disturb the hidden circuit, and you might short out a massive system in ways you never bothered to model. And finally, the grandest stage of all astrophysics. The search for life in the dark universe. We love oxygen because it is loud. It is detectable across mind-boggling distances. When the James Webb Space Telescope looks at starlight filtering through the thin atmosphere of a distant exoplanet, those spectral lines can whisper the chemical signature of O2. But oxygen suddenly becomes a far more dangerous, ambiguous clue if dead geology can manufacture it in total darkness. If non-biological processes can sustain vast oceans of free oxygen under the right electrical conditions, then finding oxygen on an alien world is no longer a guarantee of biology. That doesn't ruin oxygen as a biosignature. It just matures it. It forces us to grow up. In practice, it means we must demand extreme context. What are the co-gases? What is the geology? What is the redox state of the crust? Are there surface catalysts? For example, if we find oxygen sitting right alongside methane in an atmosphere, in a state of strong chemical disequilibrium, that is incredibly hard to explain abiotically because those two gases desperately want to destroy each other. If they are both present, something is rapidly, constantly making both of them. But even then, you never, ever want a single molecule to act as the sole judge, jury, and executioner of reality. You want a massive stack of evidence, multiple independent lines of physics and chemistry violently converging on a single truth. So let's stress test our entire model of reality with one final thought experiment. Imagine a distant ocean locked under a miles-thick shell of solid ice. Let's call it Europa, or Enceladus. There is absolutely no sunlight. There is absolutely no photosynthesis. But deep down, at the crushing bottom, the rocky seafloor is heavily dotted with metallic mineral nodules. Dark, salty currents slide relentlessly over them. Tiny, microscopic electrical potentials arise in the cracks. Oxidants and chemical fuels begin to appear in razor-thin boundary layers, swirling like an invisible, electrical weather system. Would we dare call that world lifeless just because it lacks a sun? Or would we finally be forced to admit that our search image for life was simply too small, too biased, and too profoundly human? Here is the deepest lesson of all. The scientific audit does not simply end with a neat label of "It's true" or "It's false." The deeper win is learning exactly which measurements actually deserve the power to rewrite a worldview, and which measurements desperately need stronger cross-examination. Because for generations, we have been treating certain molecules like strict verdicts. Oxygen present, guilty of life. Oxygen absent, innocent of biology. But in the rigorous theater of science, molecules are only clues. Only the complete, unbroken, heavily audited story can ever convict reality. So, where exactly does that leave us, right now, tonight, with the heavy winch still humming in our ears and that impossible oxygen trace still haunting the glowing screen? Here is the synthesis, in 3 clean breaths. First, for decades, we fully believed that free oxygen belonged almost exclusively to sunlight-driven life, and that in the deep, crushing darkness, oxygen should strictly be consumed, never manufactured. Second, stunning reports of dark oxygen being produced near deep-sea polymetallic nodules are actively challenging that deeply held expectation. But this radical claim lives or dies entirely by the strength of its controls. We must demand independent sensors, extreme pressure calibration, isolated null sites, precise flow tracking, and undeniable chemical crosschecks like dissolved gas analysis and stable isotopes. Third, if this incredible signal survives the audit, and so far, it is putting up a hell of a fight, the best physical explanations cluster tightly around bizarre electrochemistry and reactive hidden reservoirs. We must start viewing rocks as active circuits, nodules as catalytic stages, and the abyssal ocean as a vibrant place where massive amounts of free energy may be quietly flowing in forms that we simply never bothered to measure. Now I want to leave you with a contemplative takeaway. Something heavy to carry into your own life, not just as scientific trivia, but as a lens for how you view the world. Take one deep breath right now. Feel exactly how automatic it is. Your human body treats oxygen as an absolute certainty. It takes it for granted. But the universe treats oxygen as a brutal negotiation. It only appears when massive amounts of energy pay for it. It instantly vanishes when chemistry inevitably collects the debt. If something as intimately vital as our own breath can suddenly be produced by cold, silent mechanisms that we entirely fail to account for, what else in our own lives do we confidently treat like a final verdict, when it is really just a clue? And that brings us to the next great question. The heavy door that we must leave wide open. If oxygen can truly be made without a single drop of sunlight, even in microscopic pockets at the bottom of the sea, what other legendary biosignatures might actually be nothing more than the cold artifacts of geology, electricity, and deep time? And what specific combination of signs would finally be strong enough and undeniable enough that we would gladly bet our planetary loneliness on it? If you want to keep going down this rabbit hole, I am putting a video on the end screen right now. Just click it. It is perfectly designed to fit directly after this exact video, and it will push this specific question even further into the unknown. And if you want to see more high-stakes audits exactly like this one, where we absolutely refuse to just repeat flashy headlines, and instead we ruthlessly interrogate the physics behind them, then subscribe to this channel. Do not subscribe for the comfort of certainty. Subscribe because you want better doubt. Now I have one question for you, and I will be down in the comments reading your answers. If you were running this mission, and you had the budget to send exactly one additional, highly specialized instrument down to the seafloor to settle this mystery once and for all, would you send microscopic voltage probes, stable isotope samplers, highly sensitive hydrogen sensors, or massive high-pressure incubators? What would you choose and exactly why?